Yeah, you can start. I've started the
Okay,
recording.
fantastic. So it's a real pleasure to have Dr. Anand Kumar Jha with us today in an online capacity. So Anand obtained his 5 years integrated MSc in physics from IIT Kharagpur in 2002 and his PhD from University of Rochester in 2009. After doing a postdoc for about a year at the University of Rochester, Dr. Jha worked with Intel for about 2 years and then joined IIT Kanpur as an assistant professor of physics in 2013. Since 2018, he has been an associate professor of physics at IIT Kanpur. Uh, Anand has set up a quantum optics and entanglement laboratory at IIT Kanpur and carries out experimental and theoretical research works in the broad areas of classical and quantum coherence, quantum entanglement, and quantum metrology. So I will ask Anand to start presenting. And I would also ask the audience if they have questions to please use the raise hand button and I will call on you and then you can unmute yourself. So please use the raise hand button. Okay, Anand, please, the floor is all yours.
Okay, all right. So, well, thank you so much for this invitation, to give this talk as part of IISc's Quantum Technology Initiative, and also for the really nice introduction. So for this talk, the title is Partial Coherence, Applications in Quantum State Measurement, Imaging, and Communication. I have deliberately chosen this title. People who actually work in partial coherence, they are probably definitely aware, but people who do not directly work in this area of partial coherence, when we say partial coherence, sometimes it means just some very classical concept, or sometimes even that it is very theoretical concept and not much practical use. So I just wanted to kind of put this in perspective that since this is a quantum technology initiative talk, there is enough quantum stuff in here. And this is all, the way I put it, I just wanted to kind of convey, this is all from, as a result of working with, playing with this partial coherence. So this really has given rise to all these applications, at least three that I'm kind of presenting here. This is my own work in quantum state measurement, imaging, and communication. So hopefully you will, through this partial coherence, which of course is a very classical idea as it started, but the idea of coherence is pretty much the same in classical as in quantum. I hope you will see enough quantum stuff to kind of justify it as a quantum technology initiative talk. Okay, so with that, here is the outline. I'll just do a very quick intro to what coherence is, and then I'll go through some of the works that we have done in the last few years, through studying, measuring, generating these partial coherent fields. So first thing I'll kind of touch is this efficient quantum state reconstruction through coherence function measurement. The second is the use of partially coherent field for enhanced imaging and communication, especially through turbulent environments. Then I'll show you one work, experimental work, where we have shown that 2-photon entanglement that actually can be measured using a single photon detection. And here a single photon detection of like a coherence function. And finally, as a result of, this is a bonus of kind of studying partial coherence, that we kind of accidentally kind of discovered a very nice result that we got recently, which is the revival of 2-photon entanglement in the presence of turbulence. So again, now before we could really start, I just wanted to kind of bring in Emil Wolf here. This is the 100th year of Emil Wolf. He is 1922 born. He just died in 2018 at 96 years of age. He's really the modern pioneer of coherence theory, although he worked in completely classical scenarios, but he definitely has contributed a lot to classical coherence as well as quantum coherence. Many people would probably know him through these books, Principle of Optics that he wrote with Max Born, and this Optical Coherence and Quantum Optics that he wrote with Len Mandel. He actually wrote the classical part, and then Len Mandel did actually the quantum part. So in fact, I at University of Rochester, I'm pretty sure that was his last course that he gave in 2006 on coherence, and I took that course as an audit course. I didn't take it for credit. And I think I was in the third year into my PhD, and at that point I was more into quantum spontaneous emission and stuff. But after taking his course, rather auditing his course, I basically switched over to more coherence ideas and concepts. So right, so I think thought we'll just put a slide for him. Okay, so with that, let's really get started. So first, just a very quick intro to coherence as to what we mean by coherence. So coherence is basically the degree of order in any random field. It could be classical field, it could be quantum field, and so on. The ideas are very similar and analogous. So what do we mean really here? So if you, let's say I have a random set of sources that emit light, then in coherence, the typical question you ask is for a given random or partially random or fully random source, what is the correlation between the field vibration at location rho 1 and rho 2? This in a sense is a question that is being asked about spatial coherence, that what is the correlation between field vibrations at rho 1, rho 2. And to answer that question, what you do is you select part of the field from rho 1, part of the field from rho 2, and then mix it at some other plane. And then you sit at one point, let's say rho, and look at the intensity here. So before intensity, we look at the field, and the field at rho will be the superposition of field coming from here, which is rho 1, and field coming from rho 2. So these are the two fields that superpose to give me the resultant field here. Of course, omega t1, omega t2, these are the phases that the light acquires as it propagates from rho 1 to rho and rho 2 to rho. So that's the field. The intensity is the U star U ensemble average. And if I just expand it, that's how it looks. This part is the intensity. Of course, there's this factor because of the size of the slits and so on. So this, the intensity at rho, well, I can write it like this. So intensity at rho essentially has component from the intensity at rho 1, intensity at rho 2, and this cross term. This thing is called intensity or spectral density, and this function here that is called the cross spectral density function. This essentially contains all the information about coherence. In any coherence measurement, what you essentially do is measure this coherence function through this intensity measurement over here. So this is a generic setup that you do the intensity measurement, and through that intensity measurement, you try to find the cross spectral density function. That means the correlation of the field at this plane. And this is pretty much how coherence functions are measured. I have shown this for spatial coherence, but one can have a similar setup for measuring coherence in time, coherence in angle, and also in polarization. Okay, so when you are looking at the field, the intensity at this point, you will typically see fringe pattern like this. This is a very high contrast fringe pattern. If you do see, we just say this is highly coherent. I mean, this I'm just doing in a more qualitative way without actually quantifying it, but this is very highly coherent. If you see the fringe pattern like this, you'll say this is partially coherent. And if you see a fringe pattern like this, you'll say, well, it's nearly incoherent. So this is the very basic, coherence ideas. Now, I kind of wanted to put the coherence as it is understood as part of classical wave mechanics and also as quantum mechanics. And at least for one photon field, the idea of coherence is pretty much the same as it is in quantum mechanics as it is in classical wave mechanics. And here is how you see the parallel. Of course, the coherence idea becomes very different when one goes to two photon fields and so on in quantum mechanics. But as far as one photon field in quantum mechanics and the classical wave mechanics, it is pretty much the same. So when there is no randomness in the classical field, we represent it as field. Again, in quantum mechanics, when there's no randomness, we call it a pure state. The field in time, or the signal in time, can be represented as this Fourier transfer of Fourier signal in the frequency domain. Similarly, in quantum, when we have a pure state, we can represent it in the frequency basis and so on. So that's the kind of parallel I'm trying to draw. A signal in position, or as a function of position, can be written as this plane wave modes. It is the IQXX. This is one-dimensional plane wave mode. Similarly, I can have quantum state We just superposition of these plane wave modes. So that's time, that's space. One can also have it in angle. So a signal in angle can be written in this form, alpha L to the IL phi. If I go to quantum mechanics, write the state, I can write it like that. Now, this is actually connected, this angle is actually connected to this L that you see here is connected to what's called the orbital angular momentum of photon. I think many may not be familiar in this audience, may not be familiar with this. So I'll just take a very quick detour and just describe what we mean by the orbital angular momentum of light. So this is again very old stuff. You have this paraxial wave equation in cylindrical coordinates. You solve it. Solution is the Laguerre Gaussian mode, and it looks like this. There's so many things. Only thing I want you to notice is that it is e to the IL phi. The phase dependence comes only through e to the IL phi, and Laguerre Gaussian modes have these two indices P and L, so two-dimensional modes. And if you actually plot these modes, that's how the intensity looks as a function of different P and L index. And this is how the phase looks at a given Z, the L equal to 0. So I have chosen here P equal to 0, and then L equal to 0, L equal to 1, L equal to 2 modes look like this at a given Z. And if you plot it as a function of Z, for L equal to 0, it's flat phase at every plane. L equal to 1, it makes one helix. L equal to 2, it's double helix. So this is again all known, but one thing that made this very popular is this observation that in a Laguerre-Gauss mode, the orbital angular momentum per photon is actually h bar L. So this is like per photon, the orbital angular momentum is an integral multiple of h bar. Hence, and this L is basically integer. It goes from minus infinity to infinity. So this basically says that yes, this could be very useful for quantum information because for computing and other things you do need a discrete basis. So again, this was all known, but this result in 1992 really showed that this Laguerre-Gaussian basis can actually, or photon can actually be used, can have a lot of use in quantum information. So again, a lot of application for this. This is in classical communication. People have shown in the orbital angular momentum basis. You could do terabit data transmission and so on. So, but I'm just showing a few, but there are many more applications of orbital angle that has now actually come up. So just that was a brief detour for orbital angular momentum. So when you have the state in orbital angular momentum, you can take the projection in the, again, angular position basis. And when you take the projection in the angular position basis, that's a wave function. This you can compare that now these are at kind of equal footing, the classical wave mechanical field and this quantum wave function. Well, they're not the same, but at equal footing that you can see same expressions and so on. Now, this is when there's no randomness in the field, but now when there is randomness in the field, then we describe a classical field through correlation function because field description is not enough. And we write, for example, in the angle basis, we will write this as a correlation function, and the basic correlation function is this, which is V star phi 1, V phi 2. If I just use this expansion, this will have this form, and since this time we are taking this ensemble average, there is no randomness here. Ensemble average actually shows up there. For quantum, if it's a random process, we call it a mixed state, and then we write it as a density matrix. And density matrix, if you take a projection in this basis, then it basically has the same mathematical form. So this correlation function in the classical wave mechanics and the density matrix element in quantum mechanics, they are at same mathematical footing. So with that, just one particular example for this, that if here this basically shows what is the correlation between mode with index L1 and L2, and if the modes are uncorrelated, we can write it like that. And then in that case, what we find is that this correlation, this is just one special case, this is a general case, but one special case, what we find that when the OAM modes are uncorrelated, the correlation function then has this simple form. And in this analogous situation in quantum mechanics is that rho basically becomes a diagonal mixed state. And when you do have this, we call this angular correlation function. We call this OAM spectrum, orbital angular momentum spectrum. And this whole thing is called angular Wiener-Khinchin theorem. So with that basic, let me go to the few works that we have done. And then first thing I'll show is these few things we have worked out for efficient quantum state reconstruction. And this we have done a state measurement in the orbital angular momentum basis. Of course, the state reconstruction or quantum state tomography, this is this is a subject of research, experimental research for a very long time, and this is actually very, very difficult. So we have not really worked out it for a general state, but we have worked out an efficient method for special class of state, which is the diagonal mixed state. So if I have a state, quantum state in this, then there's a very efficient way of measuring it. So again, measuring orbital angular momentum, people have been trying it for long. There are several methods. Again, this is still not a complete list. It's 4 that I have put here. Several limitations. Again, let me not go through it, but just point out that these methods for measuring this high dimensional orbital angular momentum basis, this is quite inefficient because they involve too much loss, very stringent alignment requirement, and very sensitive to noise. So we came up with a method which actually bypasses all that limitations. So this is here it is. So I have this diagonal mixed state. Again, I can write the diagonal mixed state, which is of course a density matrix. I can write it like this with the condition that the correlation is of this form. So that's the diagonal mixed state. So again, I'm interchanging the classical and the quantum language. That's why I put that first slide, that the density matrix and the correlation I'll kind of be interchanging in this talk. So this is the interferometer that we came up with for measuring such a state. So what is this interferometer? The main basic aspect of this interferometer is that the reflection flips the wavefront along the reflection axis. So if I have it is the I minus IL5 mode coming in, and that's my mirror, that's the reflection axis, it just flips the wavefront. So it is the minus IL5 actually becomes it is the IL5. So phi goes to minus phi. That's what a mirror does. So again, this is just a simple Mach-Zehnder interferometer. The only thing is that there's odd and even number of mirrors. So because of this odd even combination, if this is the input to this Mach-Zehnder interferometer, then at the output, I have one term which has it to the IL5, and the second term will have it to the plus IL5 because one is inverted with respect to the other. So this is the output at the interferometer. Well, that is the field, and if I take the intensity, that's how it actually looks. Where this delta, this will be just the phase difference between the two arms. Now, you see this intensity has the first term, which is the intensity from this, second term, intensity from that, there's a cross term. So this is pretty much the same as what I was pointing out here. This was for space, first term, second term, and there's a cross term. So it is pretty much the same here. I just wanted to kind of point that out. But the main thing here of this interferometer is that the correlation function and the intensity, they have the same functional form. So if I measure this I of phi, I can figure out what the correlation function is. Once I know the correlation function, I can find out the spectrum. So that is the whole idea. But again, this interferometer will still be sensitive to background noise and so on. So we went kind of like a step further. And so this is when we don't include noise in the theory. This is what it is, that the output as a function of phi has the same functional form as this correlation function as a function of 2 phi. And once we know this, we can find the spectrum, which is what we are interested in when we do the density matrix reconstruction. So now if we do include the noise, let's just add some noise, which is the background noise and all. And with that, if we do difference intensity measurement, that means this cosine delta, we do the intensity measurement of 2 different deltas. And if delta is, let's say, any value delta C, delta D, then this difference comes out to be this. And where this delta N, that is a difference in the noise in the two measurement. And if the shot-to-shot noise is actually same, I mean, if the two measurements, I mean, the background noise is same in those two measurements, then actually this actually gets cancelled. And what we are left with is that this difference intensity becomes directly proportional to the correlation function. So if I was using it here, I need to know this K1, K2 very precisely in order to be able to measure this. But now with this difference intensity, I just need to know this, I don't need to know this K1, K2. Since this is just proportional, and I can always renormalize later. So with this, what you find that this delta I has same functional form as this, and thus we can actually measure through measuring this, we can measure this, and after measuring this, we can actually get the spectrum, which is the diagonal element of the density matrix. And since the density matrix is only diagonal, we have the whole density matrix reconstruction. Okay, so then
I have a small question.
Yeah,
so in this you're introducing extra noise in the second part, like
Yes, so the noise can be from the interferometer, which is not really the interference signal. So it could be anything apart from the
So how do you actually get rid of the noise then? Like how do you go to the no noise case?
Fantastic. So well, I'll show you something. So to answer that question, let's do the experiment. So that's my helium neon laser. I actually produce this state using helium neon laser. Well, this is a density matrix. Helium neon laser is a pure state, but on SLM, by doing the time separated, I can actually make a the diagonal state. But let's not go into that part. So yeah, one can make the state, and we'll send that state through this interferometer. And so this is my for a given delta C, this is what I see on the interferometer. So like no noise, this is what it is. But if I add noise, there will be delta, IN. And with noise, let's say this is what I see on the interferometer. And with this, if I use this, try to construct, this is the reconstruction, that red one, not very good. And if I get the spectrum, again, not very good. Then I take it at different value delta D. Again, this is the interferometer, interferogram. I actually see it. If I use this to reconstruct, I see that. Now, if I take the difference of these two, then this is what I see. You can also see this there's no noise here. And if I use that, then this is the spectrum that this is the correlation function that I reconstruct. And with that, this is the kind of match we get. So this is a very good match here. We need it for some other spectrum, which is rectangle, first shot, the second shot, difference, and the reconstruction. Well, in this case, this is not as dramatic as the other one, but it will be even more dramatic in the next example that I show. But did I answer your question?
Yeah. Okay. So actually, Vivek has a question. Vivek?
Yeah, hi Anand, Vivek. Actually, I had a very similar question to Akshay's, but I think you answered my question. I was also wondering, do you use the other port of the final beam splitter for any?
Okay. Yeah, in principle, I think either you do delta C, delta D at the same interferometer, or you could have done the other part as well. Yes, that will also work exactly. Yes.
Okay, thanks.
So since I promised quantum results here, so then we just tried if this could actually be applicable in the quantum domain. So in quantum, first of all, you have this entangled photon sources from parametric down conversion. That is really the workhorse for any experimental work, at least in optics. The state that gets the entangled state that gets produced in parametric down conversion. Well, for those who do not know, parametric down conversion is the nonlinear optical process. I think most widely used nonlinear optical process for producing entangled photons. So even if I don't go into full detail, the state of the entangled photon in the orbital angular momentum basis look like this. So this is the state of this. One pump breaks into signal idler. What you have here is that whenever signal photon has orbital angular momentum LH bar, idler photon has orbital angular momentum minus LH bar. So that is a conservation of orbital angular momentum. This is when the pump has zero orbital angular momentum, which is the Gaussian beam. So in this case, this thing is known as angular Schmidt spectrum. Again, I need to point out here is that this L that I'm showing here can go from minus infinity to infinity. So the signal photon can actually have any L value. But if the signal photon has LH bar, idler has to have minus LH bar for its orbital angular momentum. So in quantum entanglement, you actually want to make this a state with SL being as wide as possible. So that gives the dimensionality to actually kind of work with. So this SL is called angular Schmidt spectrum. And we need to kind of measure it very accurately, but the current methods that people do use involves what's called the coincidence detection, that you detect one photon here, then time cooled another photon here. Of course, in coincidence detection, very difficult. There's a lot of noise. So, but we were able to kind of apply this technique that I presented in a few slides in the last slide in this context as well. And here is how. So this is the 2-photon state of signal idler. Now, if I just take the state of the signal photon, then I have to trace over the idler mode. And if I do that, this is the state for the signal photon. This is basically a diagonal state, diagonal density matrix. So the corresponding angular correlation function for the signal photon will have this form, because just because this is a diagonal state, it will have this form, which is the angular Wiener-Khinchin theorem that I showed in that slide. So this basically says that this SL is basically the spectrum, the orbital angular momentum spectrum of the signal photon, and this SL is same as that SL, which is the angular Schmidt spectrum, that is a 2-photon spectrum. So it says that if I know the angular OM spectrum of signal photon, I can actually find out the Schmidt spectrum of 2-photon field. So that is very good news. So that I just need to measure the OM spectrum of the signal photon. So then this is what we did. You bring in the DBO, the parameter convergent crystal that produces this photon, and you make this signal idler go through this interferometer. And this is the result. That's my first shot. And this is how the spectrum reconstruction look like, little noisy. Second shot, spectrum construction, again, little noisy. The difference intensity, and this is much cleaner. And if I look at the spectrum reconstruction now, this is what it looks. So this is about 83-dimensional state that we were actually able to, 82-dimensional state that we were actually able to produce. At that point, this is certainly the largest number reported, and this we published in 2017. Of course, you see something here that says this. I mean, there's a fantastic fit, except at this point. So, so then we looked at it a little more carefully, even from a theory perspective. And in this case, we were actually not taking care of the tilt of the crystal. And so, if you include the tilt or the phase matching of this crystal, then I'll just show you the result. Then we showed that we can actually get rid of that little mismatch we had over here. So now this tilt of the crystal, that becomes a fitting parameter, and then we can match it much more nicely. And not only that, by changing it at different tilts, one can generate even broader spectrum. And actually then after a year, we reported angular Schmidt spectrum or number of 229. So this was for measuring the quantum state tomography in the OM basis. Yes.
There's a question from Varun. Varun, please go ahead.
Yeah, hi, Anand. So quick question. When you take a difference between two images, right, doesn't the variance in your noise add? Why does the noise go down? It's not clear.
Well, those will definitely happen. So here okay, so let's go back. Right. So this is just the background. So you can see it as a flat or not flat, some constant. If you just see it as a constant background, which is probably the most difficult aspect when you do interferometer, because there's always because it cannot be perfect, and there's some background and stuff from the lab or some LED kind of blinking. So this is the background noise that we have added, which does not depend on this phase difference, because this will be kind of incoherent. So this will not depend on this. So this noise, this will remain the same in the 2 shot. That means for these 2 delta C values. So this is not, again, this is not the number state, the photon noise that I'm talking about. If that answers the question.
I see. Okay. Fine.
So this is more like the background signal noise, not the not the short noise or the photon number noise that we are doing. So just the background signal. This remains flat. This remains the same at every delta C value, while this function changes as a function of delta C because it interferes. And so if I subtract, then I actually get rid of this as well as this first term, and that's how I get the advantage.
Okay. Thank you.
Okay. So. Okay, so after the diagonal state, then we actually came up with like pure quantum state in the orbital angular momentum basis. And when we say pure state, Now in this case, there's no ensemble average, there's no randomness that we have. Again, I'm interchanging the classical and quantum language. I will not go through the details of this one, but the only thing I want to kind of point out that it is pretty much the same interferometer, except in this case, we have what's called the Dove prism. Dove prism actually just rotates the wavefront. So here in one arm, we are rotating the wavefront by some angle. In other arm, we are rotating the wavefront by some other angle. And with that combination, only thing I want you to kind of notice that this is the coherence function, and these are the intensity measurements. So somehow the intensity measurements in this case at this interferometer is able to capture the coherence function. And through measuring this coherence function, I'm then able to reconstruct this quantum state in the OM basis. So using 9 intensity measurements, then and doing some reconstruction algorithm in terms of iteration, we were able to kind of, I'll show you the result. This is the result for a 9-dimensional pure state. This is how the theory shots should look like. This 9 theory shot. This is how the experimental shot look like. So it's a very good match. And this is how the reconstruction look like for the magnitude and the phase. Since in this case I have pure state, there will be phase as well. To get a better overall feel for how how accurately this method works. So this is the measurement fidelity. So if I produce a state, how close I'm able to reconstruct the state. So I mean, when I produce a state, I know what the state is. So this just shows how accurate this interferometer is. So this is the measurement fidelity. Up to 11-dimensional state, measurement fidelity is more than 90%. Then of course it decreases. So this is what we were able to kind of do for the pure state. Up to 11-dimensional state, this works with 90%, more than 90% fidelity. So, well, this came out in 2020. Now we are working on for more general orbital angular momentum state. Again, the idea is to come up with efficient methods for actually measuring it. Okay, so now let me go to the second one, which is using partially coherent light for enhanced imaging and communication. So this part right now is classical application only, and but whatever we have developed here, the idea is that then we go take these ideas and have go towards kind of in the quantum domain and do quantum metrology and quantum imaging and so on. So again, I don't want you to go through the detail. Only thing I want to point out here is that we came up with a way of generating a partially coherent state. What I mean by that is as follows. So if I have just a regular LED or bulb, the spatial coherence area from that source actually increases as a function of the propagation distance. For example, sunlight, the spatial coherence area of sunlight at the sun surface is 0, but while it kind of comes to Earth, by the time it comes to Earth, it becomes about 50 micron or 100 micron, the transfer spatial coherence length. But we came up with a source, the spatial coherence area of which does not depend on propagation. It remains constant. It is very simple idea. In this, all we do is put a spatially completely incoherent source at the back focal plane of a lens. And since a lens will convert a point source into a plane wave, what I get here, since what I have here is just a bunch of plane wave completely uncorrelated because this is spatially incoherent, what I have here is a bunch of plane wave completely uncorrelated, and that is what gives us that's what gives us coherence function that does not depend on the propagation distance. So this is the experimental result. This we did with we bought some 850 rupee LED from Amazon, 9-watt LED. So we broke it. Inside of it, this is the actual picture of that LED. You see this 9 LED, then we kind of covered all that, just had one of these open. And then we looked at the coherence function measurement, and this is how the coherence function looked like. This is not intensity, this is a measurement of the coherence function. And from 86 centimeter to about 4 meters, you see the coherence function doesn't change. So it remains propagation invariant. We did it with this kind of source as well, where we kind of cover everything except this one and that one. And this time the coherence function has this form. So this is not the intensity. This is not the intense interference. This is a coherence function that has interference. And again, even this kind of coherence function, we were able to show propagation invariance to about like more than a meter. So this was about a new way we kind of generated the state, and then we found a way of kind of measuring the state. This is very analogous to what I just showed in detail for the orbital angular momentum. Here, the inversion was through a mirror. Here, the inversion is done through a lens and a mirror. But again, I will not go through this. Also is a two-shot difference intensity measurement. And with that, we came up with a very powerful way of measuring the coherence function in just two shot. Earlier, you could actually measure the special coherence function using Young's double slit by sliding the two slits and so on, which is very ineffective. But here we were able to kind of make the measurement of coherence function. This is theory, this is experiment. Then we actually did with this source, complete in all 9 LEDs. This is how the coherence function looks like, the theory, and that's how we were able to get experimentally. So now that we had a way of generating a coherent source, the coherence function of which was not changing as a function of Z, and also a very powerful way of measuring it, we then try to utilize it for some imaging application. So here I have a source, the coherence function of which is not changing as a function of Z. So how can we use it? So so here what I'm showing is that with such a source, it falls onto this object, goes through a scatterer, and then we look at it. So it's basically imaging through turbulence. And here is the result. What you find is that, let's say if I have a conventional source, conventional LED bulb or light bulb, then the image resolution, this is the object, then the image resolution, and this is the strength of scattering. So some scattering is there. So the imaging resolution actually changes as a function of Z. Okay, where Z is the distance from the object and the scatterer. So the imaging resolution changes as a function of Z. But if I use the propagation invariant source, the one that we have generated here, then what we find, since the coherence function doesn't change as a function of Z, the imaging resolution doesn't change. And this is because the smaller the coherence area, better is the imaging resolution. Because the highly coherent the field is, there's more scattering. And that's why if you actually use a helium neon laser, which is especially fully coherent, the imaging resolution is pretty bad. And if you go to slightly higher scattering, helium neon laser with this scattering strength will not be able to kind of do the imaging. Conventional source can do the imaging at 10 centimeter, but this imaging resolution kind of dies down pretty quickly. But this partially propagation invariant source can do it with the same imaging resolution at every Z. Of course, as you increase the scattering, overall the imaging resolution decreases, but whatever it is, it remains constant as a function of Z. So that is how you could use especially partial coherent field for imaging through turbulence. We did an extension of this work, and this was like minimizing the coherence area to the minimum possible value, and then we did the imaging with that. And then we showed that you could improve things even further, even if you go to the alpha scattering, very high values of scattering. With this source, we were still able to kind of image. The conventional and the Heaney I'm not showing because they don't do. I mean, they were just not able to image anyway. So this is kind of one nice example utilization of partially coherent field, at least in the classical domain. The other thing, yes.
Anand, small question. So does the structure of the LED cause any issues, like so you have this LED, so like is it analogous to using a diffuser, what people use to improve imaging quality?
So that we have not explored. For example, if I change my LED as 1 or 2 or 9, the coherence function structure that changes. But here the only thing that we have utilized so far is just the value of the coherence area. But the structure itself we have not utilized for imaging. But yes, you're right. There's whole field, entire field for this called the structured imaging. So there you utilize the structure. Well, people have it for mostly the structure and the intensity. Utilizing the structure and intensity, you can actually increase the imaging resolution. So there must be something like that for the coherence function as well. That if I have structure in the coherence function, there should be some imaging benefit. But that we have not utilized. It is just the fact that this source has a smaller coherence length compared to helium neon or the regular LED, for example, and it remains constant as a function of Z. And so that is the only fact that we have utilized here. Yes.
Okay. It's very interesting. Actually, Vivek has a question now. Vivek?
Okay.
Yeah. Hi, Anand. Just a quick question. So Just to clarify, so the in case of the LED versus the helium neon laser, the LED has a let's say larger spatial coherence length along Z direction. But like if I think about in the transverse direction, like let's say if I did the YDSE experiment and plotted the fringe modulation depth, is that also somehow better for the partially coherent LED source, or I mean that is expected to be better for the Heaney case, right?
Yeah. So Heaney would
Okay.
be perfect. Heaney would
Yeah.
be 100% visibility.
Okay,
And
but that doesn't matter is what you're saying. Like what really matters is the Z direction.
that actually works against. So
Okay.
more spatially coherent the source is.
Okay,
It
the
is
more the scatter will
Yes.
interfere in. Okay.
yes. So if the scatter is not there, then Heaney will win. I mean,
Okay,
he
sure.
will ideally win, or other sources will be equally good. But there is no idea. Even if you don't have a scatter, maybe there are edges in this object, and that will scatter a lot. So
Okay.
especially fully coherent sources are not very good for imaging.
Okay.
So yeah.
All right. Thanks.
Okay. So the another quick thing we actually showed that again, this is follow up on the previous question, that if you have a structured field, again this is in correlation, so structured field, then if the field is less coherent, that is good for kind of communication. So here we have this, well, it is in turbulence. So if there's no turbulence, then and this is a structured field with a very high value of coherence. This is a structured field with low coherence. So when there's no turbulence, it is all the same. Everything is good. But when you have turbulence, this more partially coherent field is actually better. So very high value of turbulence, you see this is structured field. Now there's so much of crosstalk, but this one things are still separated. So what we showed here in 2020 that if you have a field that is structured in coherence function, it actually can be very good for it actually can be very good for communication mode. Okay, so now coming to another quantum implication that we actually found out for the measurement of with studying partially coherent field is that we found a way of measuring two photon entanglement with just with just single photon detection. So this is the setup. This is again same parametric down conversion, PDC, and I'm showing this cross section because when we are studying the entanglement, and here I'm talking about the continuous variable entanglement in position momentum basis. So position momentum basis, the entanglement is defined in this manner. So this is through what's called the EPR correlation. In this, what you do is you measure the conditional position uncertainty. This is like Heisenberg only, but here it is not. It is its conditional position uncertainty. That means, let's say if I have the idler already detected at yi equal to 0, or rather this should have been xi equal to 0, then the uncertainty of detecting the position of the signal, that will become the conditional position uncertainty of the signal. So this is conditional, uncertainty of the signal based on the condition that idler has already been detected. So that's the conditional position uncertainty. Similarly, you can define a conditional momentum uncertainty. And if this is less than 0.5 h-bar, if you can measure it to be 0.5 h-bar, then you can claim that yes, there is position momentum entanglement. So this is how position momentum entanglement is measured, and then people have actually shown it. But recently, through again studying partial coherence, what we came up with is that if the two photon state is pure, then of course the state of the individual photon is partially coherent or mixed, and in that case, the cross spectral density or the coherence function of the let's say the individual photon, for example, signal here, this actually becomes proportional to the conditional probability distribution. So conditional probability distribution of, let's say, signal photon. And of course, the width of this conditional distribution would be the conditional uncertainty. So coherence function of the signal is proportional to the conditional position, here momentum uncertainty of the signal photon. And the same thing goes for the position as well. So this gave us a way of measuring this conditional position and conditional momentum uncertainty through measuring this coherence function. So then here is the experiment. The experiment we set up, this was for measuring the coherence function that I've already explained. Again, too short. Measure the coherence function in position, coherence function in momentum, and then the value we were able to report was 0.0167. This is much less than 0.5 h-bar, and this is the best value reported so far. Well, this we have just done in 2022. So this is the best value of EPR correlation kind of reported so far. And again, this is because we were able to measure this coherence function very, very accurately. Okay, so last one, this is like a bonus for studying the this partially coherent field, and here we were actually doing this one, and then we kind of accidentally discovered this. And here what we see is that there is a way of reviving entanglement of the two photon field, even in the presence of turbulence. So this is how it works. So this position entanglement, I just explained that if you have the conditional position uncertainty, then you measure the conditional momentum uncertainty, and if that product is less than 0.5 h-bar, then we call it position momentum entangled. Similarly, you can have it for angle, orbital angular momentum basis, because just like position momentum, angle and orbital angular momentum, they also form conjugate pairs. And so in this case, what you will have is that the conditional uncertainty in theta angle and conditional uncertainty in L, if that product is less than 0.5 h-bar, then you can call it entangled in angular orbital angular momentum basis. So what we found is that if you look at the position momentum entanglement, starting from where it is generated from the crystal, in the position momentum basis, of course, the photons remain entangled for some time, and then they become disentangled. The entanglement is lost, and then it remains like that. It doesn't come back. But if you observe the entanglement in the angle OM basis, then it turns out that angle OM basis, again, the entanglement is lost, but it actually comes back without doing anything, just by propagation. The entanglement actually comes back, and after that, it remains intact for infinite distance, at least in principle. So here is the conditional position uncertainty as a function of Z. So, entanglement is kind of like lost. Well, again, here I showed that in the next slide. Entanglement gets lost right around here within 10 centimeter, and then it kind of remains like that. But for angle and orbital angular momentum, of course it gets lost, but then it comes back, and then this curve, then after that is monotonically decreasing. So this was a very nice result. This is theoretical. Now we did the experiment for that. This is for measuring the conditional position uncertainty. This was for conditional position uncertainty and the conditional angle uncertainty. This setup was for measuring the conditional momentum uncertainty, and this setup was for measuring the conditional orbital angular momentum uncertainty. And so with that, then we plotted the product of the conditional position uncertainty and conditional momentum uncertainty, and we showed that this product, this is the theory value, the dots are the experiments, that in this region, this is below the 0.5 h-bar, which is the limit for entanglement, that if this product is less than this value, then it's certainly entangled. Above, you cannot really claim anything. So here we see entangled, and after that, the entanglement gets lost and it remains like that. But in the case of angle OM, you have it entangled here, you lose the entanglement, and then again the entanglement comes back. So right around Z equal to 22 centimeter for the setup that we have, the entanglement actually comes back, and then it remains like that. So that is the entanglement revival just through propagation. So this was a very encouraging result. This again just came out 2 months ago. Now the question is, if the entanglement has this intrinsic property of reviving on its own, if I introduce some turbulence, can it handle that as well? So then we introduce this turbulence. This is just a blower heater, some 1,000-2,000 rupee blower heater, and because of the hot air, that introduces kind of very strong turbulence here. And with that, when we did the experiment, the same thing in angle. So this result is without any turbulence, and this result when we introduce the turbulence right around Z equal to some 15 centimeter. That's why I don't have any result before Z equal to 15 centimeter. Then you see that of course the situation is a little bad over here, but the entanglement revival trend you still see, and then entanglement does revive. So the entanglement revival, for example, here, at least theoretically, it happens 22 centimeter. Experimentally, it's kind of right over here. And in the presence of turbulence, that happens at, let's say, 35 centimeter. So entanglement actually does revive even in the presence of turbulence. And once revived, it actually stays like this. So this could actually be a very important result if we are into quantum metrology or quantum imaging, through turbulent medium and so on. This actually can be very powerful result that one can utilize. So I think with that, I come to my summary. So through partial coherence function measurement, through studying partial coherence.
So Anand, I had a quick question.
Yes.
So what determines this length scale after which it kind of revives?
In principle, infinite. But again, it cannot be infinite because so the basic.
No, I'm saying in the first case, right? When there is no turbulence, you said it comes back after 22 centimeters, right? That's what, right? But in the other case, it's 35. So I'm just trying to understand what exactly determines this length scale. So I mean.
Okay, so this particular length scale is decided by the strength of the turbulence. So if I have, turbulence is weaker than what I have here, maybe it will revive earlier. Right. If I have even stronger turbulence, that revival will happen a little later. So the turbulence is basically definitely destroying the entanglement to some extent, but then through propagation again, it is able to revive. So how much is the damage in turbulence will decide how long it will take for it to kind of come back.
Okay. So that means the noise source, the kind of noise source, for example, a white noise source would probably have a different effect than, say, a 1 over F type kind of noise source. Is that correct to say, or am I talking too much?
Yeah, well, I don't know the exact answer to that question, but here again, this is there is no photon number noise that we are talking about here. This is phase turbulence that we are talking about. That is what you see mostly in atmospheric turbulence. So and again, one thing is that we assume no loss here. So although the field is going through turbulent medium, there is no loss. So if there is loss, then this revival trend will not be there. Then it will start to come back. But as long as there is no loss, that means the detector is getting everything from here, then you will have revival for the infinite length. For this phase turbulence that you actually have. I'm not sure if I answered your question for that one or whatever.
That's fine. That's fine. Maybe I'll read the paper and get back to you.
Yeah,
thanks.
Fine. Okay, so maybe I can go to the summary then. So what I have shown a few results in efficient quantum state reconstruction through coherence function measurement, using partially coherent light for imaging and communication through turbulence. And here what we are working now to kind of take this towards quantum domain. Then instead of using partially coherent light, classical partially coherent light, we use quantum partially coherent light mixed states and see what kind of advantage we can get for quantum metrology, quantum imaging through turbulence. We have also shown you that through again partial coherence function measurement, one can actually have a measurement of 2-photon entanglement through only single photon detection. This is right now what we have is only for a subclass of state, which of course is the most widely encountered, but this is still for subclass or class of state, not for the very general state. And again, as a bonus, we also saw the revival of 2-photon entanglement in the presence of turbulence. And our next step would be to kind of see how this could be utilized for doing, actual quantum imaging, quantum metrology in the presence of turbulence. So again, with that, let me just thank these funding agencies which made all this research possible: IIT Kanpur, DST, SERB, and also this recent Quantum Enabled Science and Technology initiative, DST. And a lot of work has been done as part of that. And this is my current group. Again, the work that I presented has a lot of other members as well, but they have kind of left. Again, even from this picture, if you have left, this is not the most updated picture. And again, if anybody is kind of interested, or if students, if I mean, we are always looking for, I mean, I'm doing some advertisement here, if that is fine. So again, anybody interested in PhD, postdoc, you can check what we do, and if you're interested, that will be very nice. And finally, let me thank you all for your attention. Thank you.
Thanks, Anand, for this very, very interesting talk. Like, this is fantastic, actually. So I'm surely going to read these papers now. So questions from Anand?
Yes.
Please use the raise hand button, and I will call on you. So please, additional questions from Anand. Varun, please go ahead.
Yeah. Hi, Anand. So you showed angle and angular momentum entanglement, which is preserved over distance, right? Are there other degrees of entanglement which are also preserved?
Actually, it is not preserved. That is a very good question, maybe also a very difficult question that probably I don't know the complete answer of. So if you look at it, it is actually not preserved. So I mean, this is taken as, this is of course not a quantifier of angle OM entanglement. This is just like a verifier. But even if you just take it, the value changes just on propagation. So that is not preserved. But it kind of works out in our favor that yes, angle entanglement in the angle OM basis has this feature. So if there is an application that is based on angle OM entanglement, it can make benefit of this. So, but it is actually not preserved.
Is it only for this where you see this characteristic, or other
degrees
yes. of entanglement?
So far, yes. So if you look at the position momentum, then this is how you see it. For polarization, if you look at just this down convergent crystal, if you just look at the polarization entanglement, that doesn't change. That actually remains, I mean, if you don't introduce turbulence, if you introduce turbulence, then that will destroy entanglement, and then it will remain destroyed. It won't come back, at least a polarization. So in polarization, if you do nothing, the entanglement remains preserved, constant. Similarly, for time bin entanglement, to very good extent, it actually remains constant unless you disturb it. But actually, if you do disturb it, then it doesn't come back. Here, what we find, angle OM only so far, that even if I do nothing, the angle entangle gets destroyed and then comes back. And let's say if I introduce additional problem for entanglement through turbulence, it is able to kind of bypass that as well. So this so far I have only seen this in angle OM basis, but there may be other bases where you do have these features. That is highly possible, yes.
Interesting. Thank you.
Other questions? So Anand, I have a small question. So was this expected at all? You would have this propagation-induced revival of entanglement?
No, that's why I said it was like a bonus. I definitely didn't know. And this is just, we were just working with the coherence function for the position momentum measurement that we were doing. And then my student Abhinandan Bhattacharya, he just kind of found out. So initially I didn't believe him that, it should not be, So we spent almost 2 years kind of verifying all the results from this EMCCD based measurement. So this is definitely not expected. I definitely did not know before this, no.
Okay. So follow up to that question, does the intensity or so there is this number that you're talking about, the entanglement, but does the efficiency drop off as distance as z, and then does it become less useful, more useful, or that's the part?
So what do you mean by efficiency?
So is there loss with as they're propagating? Or is there absolutely no loss? So you have a better source as distance with distance, or that's the intriguing part, yeah.
Okay, so the only one condition, well, that is actually sometimes a very strict condition. Only one condition is that as long as I don't lose my light, this will keep on decreasing as a function of that. But of course, this is wave optics. The modes propagate, and as they propagate, they diverge, and there's nothing one can do about it. So once they start diverging, then at some point, at some distance, the aperture size of the detector will become smaller than the width of the field. And so if I don't collect the whole field, then this will start rising again. Maybe I should have had that slide. I have it in this paper. We have in the supplementary, we have shown that calculation. Okay. So once the size of this aperture becomes smaller, then just because you lose the light, you don't collect the whole field again. That's why you don't have the complete capture of the entanglement. Then it loses. But as long as this remains intact, maybe, for example, RP is saying at PRL, he has a link of 200 meters. For example, I have only shown it for about a meter, but he has a link for 200 meters. Right. So if for 200 meters, if I use a detector of large enough aperture size that I don't lose anything, then I would expect that this actually will be monotonically decreasing up to 200 meters. So that would be expectation, yes.
Interesting. Okay. Vivek, please go ahead.
Yeah, hi Anand. Two very quick questions. One is actually about the setup. So I was just curious about why do you have spatial light modulators there? And then I think the second question was, I think it relates to Akshay's question earlier. Let's say for the case of no turbulence at all, theoretically, like what determines this z equals 22 number? Is it the average angular momentum state of the input light, or is it like just curiously what determines this value in the setup?
Okay, let's go. First question is why are we putting SLM here? So, yeah. This particular, as I said, this particular setup was for measuring the conditional position and conditional angle. This one was for measuring the conditional momentum. This one we had to build it separately. Well, this part was same. We made sure it is same for orbital angular momentum. Because we could do coincidence detection using EMCCD for position, momentum, and angle, but there's no way we could do coincidence detection for orbital angular momentum because there's no orbital angle sorter that one has. And so this is, you see, this is a single photon detector with this single mode fiber and so on. And then you use this SLM to detect. So for example, I have this histogram kind of thing here. So what we do is put this SLM and put a hologram of, let's say, L equal to 5. And we'll put a hologram for L equal to 4. And with that, with this in coincidence, then I can detect what is the probability of detecting a photon, this signal photon with orbital angle 4 h bar, ideal photon with orbital angular momentum, 5 h bar. Well, the example that I've chosen, it will be 0 because it should have the very good energy conservation. But let's say if I have 5 and minus 5 here, or 1 minus 1 here, you will have the highest probability. And that's why you see this diagonal elements being lit up. So this is for measuring this orbital angular momentum one by one that we put this SLM. Hopefully, I think we are also working on that. Hopefully, in the next 1 or 2 or 3 years, we should have a way of measuring the orbital angular momentum without using SLM in a much more efficient way. But this is right now, this is the only way one can actually measure orbital angular momentum. Your second question was, how decides this? Yeah. The short answer is I don't know. I mean, this is numerically calculated, so I don't really have a very good, answer or intuitive answer actually as to, what decides it. So, I mean, in this paper, we have worked out some intuitive pictorial version as to why it starts decreasing. But what decides this number, I will not have very good answer. Of course, you have the crystal, so there's the phase matching mostly decides this. But then exactly what is the relation, like thickness or the refractive index and so on? What is the functional relation for this? That I don't know.
But do you think it could probably be tuned if we tune the
definitely
properties of crystal? Okay.
Yes, definitely. So that we can see that if we use different thickness, I think this Z changes. But exactly what is the functional form, that we don't have.
Sure.
At this point, this is just a numerical result.
Sure. All right. Thank you.
Akshay, please go ahead.
Yeah. So this turbulence, as you call it, it's just a hot air blowing. Is that what you said?
Yes.
Okay. So for example, if there is some coherent motion in the path of this thing, will that produce a completely different result, or
what do you mean by coherent motions?
Say I work with mechanical objects which vibrate, right? If we put that, and if there is no loss while this is passing through this, and in what way would it change? I'm just trying to understand.
Okay, so this one is for destroying. I mean, here we have not looked at the temporal coherence, but this one is for destroying the spatial coherence. But when I say destroying, partially destroying, not fully destroying. So if I think there's a mechanical vibrator, and again, if that mechanical vibrator is vibrating like this in a flat, then I don't think it will do much. But if the whole membrane has a different vibration at different point in a very random manner, then that will decrease the spatial coherence, and that will have a very similar effect like this. Yes.
I see. Okay. Okay. Thanks.
Okay. If there are no further questions, let's thank Anand for the fantastic talk. Please use the applause button. This is the best we can do on this virtual platform. But yes, Anand, please make a plan to come to IIC. It would be very nice.
Yeah, sure. Yes.
Great. Okay. Thanks, Anand again, and
Thank you so much.
Okay. Bye.
Okay. Bye.